In this chapter, we're going to talk about acids and bases. Acids and bases are in our everyday life, and a lot of times we don't even realize it. So these calculations and reactions and properties and characteristics we're going to talk about are extremely important. Like I said, they're in our everyday lives, and we don't always really realize it. So first thing we're going to talk about is just some common acid properties, and then eventually we'll get to base properties. So what are some common properties and characteristics? That's the first thing that the section begins with. Okay, so a lot of those you can kind of read, and some of them you may be familiar with, some of them not as much. Okay, so you can look at those, and the first lab will do. We'll get into a lot of those details. Okay, so become familiar with that. Second thing is we got to come back and talk about acid nomenclature. How do we name acids and how do we write their formulas? This is something we did do in Chapter 7. Okay. So in 7.1. So you're going to have to go back and review that if you want to. And again, you can get the video notes out on that. But the acid nomenclature, we have a binary acid. It's hydrogen and blank. So in those cases, those would all be hydro blank ic acid. Then we have oxyacids, hydrogen, something else, and then oxygen. And if you notice there's just a subscript on N. The number of oxygens can change. So that name is based upon that polyatomic ion, meaning that's SO4 is sulfate, so sulfate in an acid becomes sulfuric, and so on. Again, there's a lot more detail in Chapter 7, Section 1 to look at. Quick reminder, again, of some of those polyatomic acids. You can see there on the left-hand side in the red is the polyatomic ion. The first one's sulfite. The second one is sulfate. See this corresponding name in red on the far right. So then if an ite is in an acid, it becomes OUS. So sulfate becomes sulfurous acid. Sorry, I think I said sulfate. Sulfite becomes sulfurous. Sulfate in an acid becomes sulfuric. And so on and so forth down the line. The hypos and pers stay in line also. The last one we'll talk a little bit about a lot in this chapter is acetic acid. It's a main acid in vinegar. It is the acid in vinegar. We can write it one of two ways. You can see CH3COOH, and that's its structural formula. Okay, that's what we have right here, its structure. But then we also have it written kind of as a condensed formula. And if we notice there, HC2H3O2, C2H3O2 is acetate, 8. So 8 in an acid becomes ic, acetic. So again, very, very quick review of acids in terms of nomenclature and writing formulas. Go back into the Chapter 7 notes and videos, and you can get more detailed explanations if you need it. All right, so again, page 470, then it talks some general characteristics and properties of 5 very, very common acids. We'll talk a lot about these acids. Some a little bit more than others, but these are commercially very commonly used, also very commonly used in high school science labs and college chemistry labs and things like that. Okay. So again, you can read those common acids. I'm not going to ask you crazy details about each one of those, but it's kind of interesting to know where what some of their characteristics are and the reasons why they're very commonly used. Again, just introductory stuff about acids. So now we're going to go through the same thing about bases. On page 471, they talk about general properties and characteristics of bases. Some of them we are familiar with, some of them we're not. Okay. So again, if you're not familiar with some of them, make sure you're reading that section and you do become more familiar with them. Now, as far as bases, what chemicals are most bases? Most bases are metal hydroxides. Remember, OH is hydroxide ion. Okay. So these are all bases. NaOH, KOH, calcium hydroxide, magnesium, and aluminum. Those are 5 very, very common bases. Again, are there other bases? Yes, but these are the most common ones. The naming of these is easy. We don't have to spend any extra time on them. We just know they're metal hydroxides. All we got to worry about is the charges to balance those out. Now, there is one other base that we do need to talk a little bit about because it does give us some confusion in terms of its name and its formula. And that base is ammonia. Right? Now, ammonia is a base itself. It's a weak, what we're calling a weak base. It's in a lot of cleaners, it's in fertilizer, and those types of, and other uses. So what we got to be familiar with is if we say the word, if you see the word ammonia, it is specifically talking about NH3, and it is a standalone chemical compound. Now, if you see the word ammonium, its formula is NH4 plus. This is an ion. It is part of a chemical. And again, I think we briefly mentioned this in the nomenclature stuff. So ammonium, it's not a chemical, but we see it often paired with other things like ammonium hydroxide. Here's ammonium, and there's hydroxide. So we see either one of these three names, we've got to know the difference between them. Otherwise, we're going to get really confused and have some bad formulas, and that's not good. We'll come back, we'll talk more about ammonium and ammonium hydroxide and ammonia in terms of reactions in a later section. All right. Next thing, the definition of an acid or a base. Well, what makes a chemical an acid, or what makes a chemical a base? There's actually three different definitions. The first one is what we're going to call Arrhenius acids and bases. And this is the most common way that we define or that we know acids and bases. An Arrhenius acid is a chemical that produces hydrogen ions or is a source of hydrogen ions. Now, doesn't mean just because it has hydrogens in the formula it has to be hydrogen ions that will dissociate, dissolve, or ionize to give us H pluses. So we got to just kind of watch out with that. An Arrhenius base is a chemical that produces hydroxide or a source of hydroxides. Again, the same concept. They're going to dissociate, dissolve, or ionize to make hydroxide ions. That is the definition of an acid, and that is the definition of a base. So if we look here, if we think of HCl, and we said if HCl were to ionize, the hydrogen would separate from the chlorine. We have just produced a hydrogen ion. It has separated itself. Okay? HCl is a source of hydrogen ions. Sodium hydroxide, if that were to dissolve, the sodium's ion would separate from the hydroxide. We have produced hydroxide ions by dissolving that chemical, or the dissolution of that chemical. That's the first definition. Okay? It's the most important one. So as we go through future things, we want to look at a chemical form and say, okay, can that chemical dissolve to make hydrogen ions or hydroxide? Can it ionize? Can it dissociate? From that chemical, can we get H pluses or OHs on the right-hand side? So if we want to get H pluses on the right-hand side, then it's an acid. If we end up getting OH minuses on the right-hand side, then we know we got a base. Simple as that. Now, the last two things that we're going to talk about here are really important because this gets us into the next chapter with acids and bases and some calculations. The next thing we want to talk about is the phrase strong acid and weak acid. And bases will apply the same way. A strong acid is one that's a strong electrolyte. A weak acid is one that's a weak electrolyte. This does not mean concentration. Okay? Not concentration. Doesn't mean it's, dangerous. So to define this, so a strong electrolyte, if a chemical is a strong electrolyte, it will dissociate or ionize 100% of every particle. So if I have 10 salt crystals, salt structures, all 10 of them will break apart into Na pluses and Cl minuses. If I have 10 HCl's, all 10 of them will break apart into H pluses and Cl minuses. We could also say, if we imagine here, if we add this plus water, those H pluses really are on top of or bonded to the water. Okay? And we'll talk more about that as we go in this chapter, that that H plus isn't really loose alone. It is actually bonded to waters. So again, our point here is to recognize that this is a strong acids do the same thing as strong electrolytes. All we're trying to prove in this example. Now, a weak electrolyte is one that only partially dissociates. Now, when we say partially, how much? It depends. And it depends on something we call the equilibrium constant, KEQ, which is a huge chapter in AP chemistry, which we're not going there, but that will determine how many break apart or how many dissociate. To just give you an example, let's say I have 10 of these. Maybe what happens is, of those 10, 3 actually break apart, and then we still have 7 left over. Okay? So really we have 10, 3 break apart. We have 7 that never did. Same thing here. We could have maybe 20. Again, same chemical here. It doesn't matter how we say this. This is acetic acid. That hydrogen still is going to break off. But if we have 20 of them, maybe 10 break apart, and maybe 10 stay together. We do not need to know how many. We just need to know that only some of them break apart. That's all we care about, is some, not all. Important key here. Weak electrolyte, weak acid, weak base. Some, not all. Okay? All right, so how do we know what is or what isn't? Real simple. A strong acid kind of breaks apart like we show there, sort of a generic equation. And again, X could be a couple different things. Strong base, a metal hydroxide, that's how it breaks apart. And here's the only thing that we've got to know. It's pretty well understood that there are considered, for our purposes, 4 strong acids. So that means those 4 acids will dissociate 100% of every structure. These are the strong bases. Every group 1 and group 2 metal will dissociate 100% of the time. All others, as far as we're concerned, are weak. That's all we've got to remember. 4 acids and the group 1 and group 2 metals are strong acids and bases. Everything else is weak. Everything else is partial dissociation. And then that helps us here. Okay? We said if it's strong, they're all going to break apart. There's only a few that do that. The majority are weak, that do not completely dissociate. Now, the last thing here that we mentioned, strong does not mean dangerous in terms of acids and bases. Concentrated means dangerous. I could have a concentrated weak acid. That's very, very dangerous. I could have a diluted strong acid, and that's not dangerous at all. So it's very important that we know the difference there, because what determines dangerous is the molarity of the chemical, not how it ionizes. So again, I'm sure we'll talk about that in class a little bit. But that gives you kind of some introductory information on acids and bases, which we will be doing a lab before we get too far into this chapter.